Anyway, so he's one of our sort of nuclear theory group professors, and has been thinking also a lot about applications in that realm with quantum computers. So with that, we're really pleased to hear what he has to say.
All right, thank you. I'm supposed to put this in my shirt, I suppose. Can you hear me? I don't think I need a microphone at all, but there is Zoom. So.
We can hear on Zoom.
Omnidirectional.
All right. So yeah, quantum computers and quantum field theory. From the outset, let me tell you that simulating quantum fields in quantum computers is a very long-term project for young people. And there are many, many, many things one has to figure out. And I'm going to talk about a tiny subset of those. So don't complain to me if your research or if your things that you think about are completely bypassed here. It's not because it's less important. It's just because I don't have anything interesting to say. But just to set up the context here, let me remind you that quantum field theory, pretty much all physics can be described in the language of quantum field theory. So for relativistic particles, where the number of particles is not conserved, is a completely essential thing. And that's where I come from. But even many body physics, where the number of particles is conserved, it's still very interesting or very convenient. And it's been used for 100 years, the formalism of quantum field theory. So the scope here is extremely broad. Quantum field theory, in case you're not familiar with it, I'm looking for my students here. There's nothing to be afraid of. The same way that in regular quantum mechanics, you have positions, and in quantum mechanics, you end up having a wave function that's a function of those positions. In field theory, you're going to have a field that evolves in time that depends on space, and one or more fields, and you end up with a wave functional that depends on that. This is not the language, the Schrödinger picture is not the language that's usually used in quantum field theory, but it is the language that's going to matter to us. So for example, you can hit this wave function with operators. Like, for example, there is a field operator that does like position does in quantum mechanics. There is like a canonical momentum operator that's just like canonical momentum in regular quantum mechanics. So there is really nothing much to, that's different from the usual formalism of quantum mechanics. So if you're not familiar, you don't care about quantum field theory, you can easily follow this talk. Now, a big motivation, at least for me, to study quantum field theory is that it describes all fundamental interactions. So the standard model is set up in the language of quantum field theory. And that includes electromagnetism, and consequently the whole of condensed matter, and weak interactions, and quantum chromodynamics. Usually when people say quantum field theory, they immediately think about Feynman diagrams, and that's because there are field theories that are perturbative, that you can use perturbation theory, and perturbation theory and field theory is best described in terms of those funny graphs. And people calculate all those things. Those are not only drawings. Someone on this earth actually calculated those things. And it's painful, but it works if the theory is indeed perturbative, like it is with QED. It does not work, though, for the interesting cases. Or maybe I should say the interesting cases are the ones for which this does not work, right? Let me tell you just a few phenomena that, from my corner of physics, that are described by non-perturbative field theory. Well, the pictures speak for themselves, right? Nuclei, supernova exploding and neutron stars and nuclear reactions and stars, and even a single proton isolated in empty space has a complicated structure in terms of quarks and gluons that's entirely non-perturbative. We have the theory for this. It's QCD, it's part of the standard model, but in the last, for over 50 years, and we haven't really been able to solve. We advanced in many aspects of this, and some others are completely open still. Like, for example, understand the matter in a neutron star. It's a completely open problem, despite the fact that we know the Hamiltonian, we know the degrees of freedom, and we had 50 years to think about. So here we go. I wanted to say here that QCD that happens to be my field, would benefit enormously from having a non-perturbative method to, to solve it. Now, there is a method to solve it that's pretty general, and that goes under the name of lattice Monte Carlo. It's not going to be the subject of this talk, but it's like something we have to measure ourselves against. Quantum computers have to do better than that. So what is that? That's the following. I can formulate quantum field theory, just like it can do in quantum mechanics, in terms of path integrals. So in case of a field theory, you can write expectation value of any operator as some complicated integral. It's an integral over an infinite number of variables. So you have to integrate over all values of all fields at every point in space. For technical reasons, this has to be done in imaginary time, not in regular Euclidean time. This is very common in quantum Monte Carlo. People always work imaginary time. So how do you actually compute this numerically? Well, the trick is to realize that this is sort of like a statistical average, where the probability is given by this exponential of the Euclidean action. So the method essentially is the following. I go out and somehow I find a bunch of classical field configurations that I called phi that are distributed according to this probability distribution here, e to the minus s, just like one would do in statistical mechanics. So I even have a drawing here, a picture of an attempt at showing one of those configurations. Well, then you take the average of your observable among that subset of field configurations. And this very simple-minded idea, well, it's very difficult to carry out in practice, but people do it, and it kind of works. In fact, in the case of QCD, we found out that if you collect a few hundred of those configurations, that's enough to give you percent level precision. Of course, I'm not going to talk more about this. I'm just going to say it works, and it works more than anybody would expect. Famously, Ken Wilson, who kind of invented this whole thing, 20 years ago went to a lattice conference and said, give up. I did some calculations, I did some estimates. This is never going to work. Find something else to work on. And 5 years later, people had this picture here. It's a bunch of observables that are very complicated, hadronic observables. And look at the precision level here. And this is old, actually. So we can predict all those things and many, 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 many more. The cost, and that's the important thing for us here, is the cost of those calculations. Well, it's really high, okay? The biggest supercomputers on Earth that are not secret do this kind of stuff nowadays. But it scales with the volume just linearly. It's as good as you can possibly imagine. Some people say that it's v to the 5/4. Let's not get into that, okay? The cost is just pretty reasonable, okay? There's a huge prefactoring front, but so what? You know, computers are going to get better, and that's what'll happen. It's not exponential the volume. So you've heard this a billion times, that quantum systems have a Hilbert space whose dimension is exponential on the volume. Consequently, the Hamiltonian or any other operator is a matrix that's going to be exponential on the size, on the volume. And then any operation you do with those matrices is going to cost an exponential amount. Okay, so this is simply not true. Quantum Monte Carlo bypasses that by far. Yeah.
What space?
Yeah, the actual, so yeah. So if the spin system is the number of spins. If you're doing a fluid, is the actual volume bucket where you have your fluid. For the relativistic stuff, is actually the space-time volume that counts.
Like number of degrees of freedom.
Yeah, that would be a better way of describing. Now, let me point it out that there's a little lesson to be learned here, since there are young people in the audience. This process of making lattice QCD work to percent precision took 50 years, maybe a little more, and eventually became a spectacular success. So for a long time, people joked about that lattice QCD is going to work 10 years in the future. Well, those 10 years eventually came. So there is hope for that. The other second lesson is that the success came through a combination of improving hardware and better algorithms. And by algorithms, I don't mean the kind of algorithms that a computer scientist would care. They're all algorithms based on the physics. They're insights into the physics of the problem that led to things that are order of magnitude faster. Also, of course, as you probably know, the improvement on hardware were pretty unrelated to that. They're mostly driven by video games. Okay. So all those lessons, I think, are going to be relevant for quantum computing. I'm sorry, I need to.
Was there one or a few big breakthroughs, or was
Ooh, I can't censor that in public without picking a fight.
well, what would other?
So there's a steady thing. Yeah, other people with good common sense, but are, they would say that the main things were this. First, there's a steady developing hardware that probably you guys know better than I do, specifically to QCD. As you're going to see, we're going to have to discretize space-time. And the finer the lattice it is, the more expensive our calculation is. So people found out ways of approximating QCD very, very well with very coarse lattices by basically having more complicated Hamiltonians. This goes under the name of improvement, and it's very much in the spirit of the original Ken Wilson critical phenomena parameterization group point of view. So this is a few orders of magnitude. The best algorithm to do any kind of Monte Carlo was invented by QCD people. It's called hybrid Monte Carlo. Outside of physics, this is called Hamiltonian Monte Carlo. They don't even know that physicists invented that. That's another big one. Am I missing something else? There are many, many other smaller things, but I think improved actions and hybrid Monte Carlo, I think they're deserving of a Nobel Prize, really, because they are completely non-trivial things that actually made something work. But in theory, it's not that easy. Okay, most things don't work. All right, so that's great, right? But so is no perturbative field theory completely solved now? Not at all. There are very famous problems where it's safe, or situations where it fails. First one, in the case of QCD, imagine that you have not one proton, but 2 or 3. You want to do nuclear physics. And what happens is this. The things you would like to measure, it happens to be a correlator, and this is imaginary time evolving. It's a generic feature of those correlators that the error bars start very small and then they explode exponentially. It turns out that what's physically meaningful is not the value of the correlator here, but the asymptotic value. That's why nuclear physics hasn't been solved yet. Otherwise, it would have been. So that's one problem. Second problem. Suppose you don't have 1 or 2 protons, but I have a lot of them. I want to study nuclear matter, or maybe I want to study dense matter like it's found in neutron stars and things like that. Then I have like a macroscopic number of variants. To no one's surprise, there is a horrible signal to noise problem. In that case, it's called the sign problem, and it's very common occurrence in other models, like famously the Hilbert model wavefront half-filling. So there are very fundamental problems in physics that fail because quantum Monte Carlo fails in those situations. It fails so badly that I couldn't find a decent picture on the web to demonstrate that. So I had to run myself a little toy model and to show you these enormous error bars. These tiny error bars are tiny because the error bars are so large. The error on the error bars is enormous. So sometimes you get these tiny little error bars. The correct answer is down here, by the way. Okay. So that said, okay, for people who want to use QCD to do astrophysics, to do nuclear physics, it's kind of a non-starter. Finally, all those calculations are done in imaginary time, as typical in quantum Monte Carlo. But we like to do things in real time. There are all kinds of observables, not only non-equilibrium stuff, but even equilibrium stuff that, like transport coefficients, viscosity, and heat transfer coefficient, how do you call that? Conduction, et cetera, et cetera. All those things depend on real-time information. If I try to do my Monte Carlo in real time, it's not that the sign problem is bad. It's literally, the error is infinite. The statistical error is literally infinite. So again, it's a non-starter. There are ways people try to do this, including myself. I'm not talking about that for a reason, okay? Let me point it out that you could imagine, say, well, so in this case, Monte Carlo doesn't work. Go down to do something a little more trivial, like, for example, pick a basis, write your Hamiltonian, diagonalize your Hamiltonian. But of course, the cost of that is going to be exponential on the volume or number of degrees of freedom. Okay? So again, it's a non-starter. So I say this just to say where the opportunities for quantum computing are. There is no point in coming up with schemes to do quantum computation of things that are much more easily done with Monte Carlo in my laptop. Okay, but there are situations where that's not the case, and you should always, at least in my mind, keep an eye on this. So, how would you use quantum computers to do this? Well, God knows. I mean, we're going to find out in the future. But the standard paradigm that most people think about, and that's what I'm going to be basing myself is in the following schema. Somehow, I'm going to take the degrees of freedom of my field theory and code it up into a quantum register. And somehow, I'm going to prepare that state, the initial state, to represent some initial state of my system. Now, I'm going to study the time evolution of my system by splitting out the time evolution in tiny little pieces. And the advantage of this is that if delta t is small, so the time steps are small, I may actually be able to approximate each one of those exponentials by a certain evolution that can be written in terms of quantum gates. I cannot do this. If I could do this for the whole evolution, well, the problem would be solvable. I don't need a quantum computer. But in a lot of situations, you are able to do this approximately for small delta t. So the idea would be, of course, you code this up in terms of some quantum gates, and you apply repeatedly that set of quantum gates. And I don't know here why I have different ones. Yeah, because I'm stupid. Supposed to apply the same one repeatedly, okay? At the end, I'm going to have a wave function, and in principle, I can measure whatever I want. This includes, again, the whole physics, because that's what you do in a lab, right? You prepare a system, it evolves, and then you measure it. So in principle, if I know how to do this, I will know how to do everything. What is the advantage? The advantage is here. If the number of gates necessary for a single step does not scale exponentially with, say, the system size, it's just a polynomial, then I can do those things as expensive as it can be, as difficult as it can be, but the cost is not going to grow exponentially with the volume. And that's different from the exponential gap that you get by direct diagonalization. Also, this whole evolution is already done in real time. So all those problems that I mentioned before, you can track down to the fact that you're using imaginary time. So those problems don't even pose themselves, they just evaporate completely. Of course, every other problem in the universe is going to come in, okay? But that's the setup here, okay? So the promise of a quantum advantage in this setup hinges on the fact that I'm going to do a time evolution by a tiny step in a way that's doesn't cost exponentially with the volume. All right. All right, so let's try to do that, right? First step, I take my field theory, and a particular quantum state of my field theory is going to have to be mapped in a quantum register. And the problem is obvious, right? The Hilbert space of a field theory is infinite dimensional. My computer is not. Yeah.
That b to the power n polynomial, does that apply to just one block?
Yeah, because
Yeah, so many blocks.
yeah, so say you have 1,000. It's a fixed number, 1,000. You could find out that you need the number of steps that you need, the time steps, grows with the volume. Then it'll be a problem.
No, so v to the n is the number of gates, the repeats. It's not.
No, I'm saying that as you increase the number of volumes, you have to code that up the one time step in gates.
Yeah, v.
Okay, so the question is, how does the number of gates grows with the volume?
Not the repeated gates.
Now, the repeating costs nothing. I do 1,000 steps, costs 1,000 times more. Big deal. compared to the exponential costs. Yeah, that's what I meant. It's polynomial as opposed to exponential.
Large number of steps.
So it could be that in certain limit that you're interested, the number of steps has to grow with the volume. Then you have to take this into account too. That will be an extra problem. So that setup that I suggested, that's what everybody uses. It's not a proof that you can do that there's a quantum advantage there. It's just a hope. There's hope for it. Okay. Anyway, so the issue is how to pack an infinite dimensional Hilbert space in a finite register. And let me point it out that there are three ways in which the Hilbert space of field theory is infinite. First, there is a variable for every point in space. And space is very large. In principle, infinite. So that's infinite number one. Then, even a tiny little piece of space, like this much, there's an infinite number of points inside that. That's infinite number two. That's a ultraviolet infinite. Finally, even if I had a single point in space, and my theory contains bosons, the Hilbert space would be infinite dimensional. There's the empty state, there's the one boson state, the two boson state, all the way to infinity. So there are three ways that the Hilbert space is infinite. The good thing is that the first two are nothing new to us. Lattice field theory has to face those problems, had to face this for 50 years, and we know everything about it. Okay, we have lots of experience. There is theoretical, there is numerical evidence of how things work. In fact, taking all those limits became like a very Baroque art in the last 10, 20 years. The last problem, though, doesn't really have an analog in lattice field theory. I mean, you can try to push an analog, but I decided not to. Anyway, nobody had to face this before. So this is a kind of a novelty here. I'm going to be concentrating myself on this problem. So for all the problems that are to do quantum computation for quantum field theory, that's what I'm going to try to resolve. Now, the reason I concentrate on this particular problem is because I think this threatens any possible quantum advantage you may have in the future. So I'm not picking this problem just because I like it. Very good. Yeah. So all field theories that interest me have bosonic degrees of freedom. So the Hilbert model doesn't have one. So if you're trying to do the Hilbert model, don't worry about that. But if you want to do any gauge theory that describes fundamental interactions, the gauge fields themselves, photons and Ws and gluons, they're all bosons. So there is no way around that. Now, the way that we figure out how to deal with this infinites here, these two first infinites, and by we I mean, not me, it's royal we, right? It's going to help clarify how to figure this last problem too. So let me say a word of how we do that. The way we do this is the following. We discretize space or space-time depending on your setup, okay? The lattice is a figment of our imagination. You'd like at the end to take the continuum limit, make lattices that are finer and finer. At the same time, you want to study objects, a proton, a neutron, or maybe a duck. So say that you have a particular Hamiltonian that may depend on a bunch of parameters, and you do a calculation, and you find out that there is a duck of this size. Now you want to make your lattice spacing smaller. Well, if I want my duck to be the same size, it's going to have a size that's like 4 lattice spacings now. So I cannot use the same Hamiltonian. The Hamiltonian now is going to have to change to some different values in such a way that now that the duck it produces is 4 lattice spacings wide instead of 2. A consequence of that is that you're going to be looking for tune your Hamiltonian in such a way that the physical objects, ducks, wavelengths, masses, in lattice units goes to infinity. So all your correlations have to be much larger than the lattice. What's very intuitive if you're looking for a continuum limit. Right? You want your correlations to be much larger than lattice spacing because the lattice spacing is just a granularity that doesn't really exist in the real world. So that's what you have to do. As you take the continuum limit, you have to tune your Hamiltonian to a very special value of the Hamiltonian that has this magic property property of producing objects that are like infinite in size compared to the lattice. When you do this, you discover the following interesting fact that's very familiar to anybody who knows about critical phenomena. You can start from different Hamiltonians, say this one and that one. There's a tilde here. Okay, this one here, I have. The pointer is really pointing in another.
It's just this relative direction, not natural.
Relative to what? Oh, I see. Got it. Goes by dead reckoning, essentially. So after half an hour, I'm completely off. Oh, yeah, fine. So what was I saying? Yeah, so I start from this Hamiltonian, has some couplings, and I have to tune those couplings very specially to get something, to get a duck. A different Hamiltonian that my friend picks has to also be tuned in its own special way to get the same duck. And what you learn is that many different Hamiltonians, if properly tuned, produce the same continuous duck. So there is an enormous flexibility here in picking different Hamiltonians, as long as you do the tuning properly. In other words, there's a larger degree of universality. That's the perfect analog of universality in critical phenomena. It's the same thing, of course. Why is that important for us? Well, this is applied to discretization in space or space-time. Can you apply the same ideas to the discretization that I have to do in field space? The fact that my field space was infinite dimensional, even if I had a single point. Well, there are answers that I know, there are answers that I don't know. I'm going to tell you about solid stuff that I know. And for that, I'm going to take a toy model. I know everything about this discretization in this case. So let me quickly go through it. This O3 sigma model is a workhorse of field theorists. It has only one space dimension and one time, but has all kinds of cute properties, like it doesn't optically free like QCD, as will become relevant in a little while. So it's a little toy model for QCD if you want. The field itself, the model itself is this. In every point in space, you're going to have a unit vector. And the unit vector can move around. It's like a magnet, really. Nothing more than that. If you want to do a quantum theory of that, well, if I have a single space, I would have a wave function that depends on one single unit vector. Of course, if I have many points in space, my wave function depends on different n's, one for each point in space. The Hamiltonian for the model is just this simple thing here. There is a nearest neighbor interaction. The depend on the sign here, I put a plus, but arbitrarily, may either favor parallel spins or parallel ends or anti-parallel. And there's a kinetic term that looks like a kinetic term. Okay. If you're a particle physicist, you've never seen the sigma model written in this form, but you can do it in your head. That corresponds to the usual action that one writes. This model is solvable. In fact, the guy who solved it just got a prize. Zamolodchikov got some big prize, millions of dollars last week. Anyway, the physics can be described more or less like this. This is supposed to be a distance. A is like a lattice that I have to use. All the physics that happen at the scale of the lattice or smaller, it's non-universal. Depends how you create your lattice, and it's not real anyway. Okay, it's a lattice artifact. Wrong. The only physics that's universal is a distance that are much larger than the lattice spacing, as you can imagine. Now, this theory has something very special. Even though you look at this Hamiltonian here, and you can count, and G is dimensionless, there's a dimension of nothing. There is a particular mass scale or a distance scale that's characteristic of this model. That's very much like QCD. In QCD, the mass of the proton is not like the mass of the electron that comes from the Higgs. It does not come from the mass of the quarks. That's a tiny contribution. It comes from gluons interacting, and the gluons interact with a coupling constant that's dimensionless. Nevertheless, for reasons we can get into, you end up with a scale. That's the hadronic scale, the typical size of protons, neutrons, et cetera, et cetera, et cetera. So this model has that. In fact, the only difference from QCD is that instead of having a lot of resonances that you can fill a book with, it has only a triplet of particles with this mass, and that's it. It's a simple model. Yes.
Is there like, is it just because you couldn't fit it on the page, or like between A and then the start of this kind of shaded area?
Yeah.
Actually, is there like a reason for like, the universal behavior not going
Yeah.
away?
So it's universal for distances are much larger than A.
Okay.
Much larger for me means this.
So it's not really like a hard cut.
No, not at all. It gets better and better. I can be more precise about this, but I won't be.
Does this have to, is that what asymptotically free means, or is that?
It's very much related to it, but no, we can talk about later. It's a very subtle thing. All right, so the issue is this. Like any bosonic theory, my wave function is going to depend on continuous variables, so the Hilbert space is infinite dimensional. I can't put this in my quantum computer, so what does one do? There are three methods of truncating the Hilbert space that are used in the literature, I think, to my knowledge. Number one, take your sphere and approximate by a set of points. Now, you don't want to pick random points. You want to pick the points like well distributed around the sphere, right? So well distributed things were figured out by the Greeks. There are 5 ways of doing this. Those are the 5 Platonic solids. So you can pick one of them, and you can try to study the model where n can only take values on the vertices or the faces of Platonic solids. Long story, 30 years story, I'm going to summarize in one transparency. This has no continuum limit. There is nothing you can do to the parameters of a Hamiltonian that you ever create correlation lengths that are very large compared to the lattice spacing. So this model exists in the lattice. It describes no continuous physics. So that's a bad start, right? Now, the reason I'm not going to explain why this happens is because I have better. I actually try to do the same thing, not with this silly two-dimensional model, but with actual QCD. Or to be honest, QCD without quarks, just gluons. But with the full SU3 group and the whole shebang, okay? This is a big calculation. This is not a toy model, okay? This is supercomputers here. So what we did was this. People do calculations SU3. I've been doing this for 50 years. We said, well, let's substitute SU3 by a discrete subgroup of SU3. And you pick the biggest one there is. And that's a very important thing. There is no bigger group that I could use to approximate SU3 any better. This is the biggest that exists. Just like the Platonic solids that are 5 and only 5, there are a finite number of those subgroups of SU3. Anyway, I did gauge theory with these things using regular lattice Monte Carlo. So let me guide you quickly through this graph. This is supposed to be the lattice spacing. 0 here is the continuum limit. On the y-axis, we have some physical quantity. It happens to be the critical temperature for the confinement. It doesn't matter. It's a physical observable. Then someone does a calculation with regular SU3, and they get these points here and extrapolate to this. Someone else uses a different action, a different Hamiltonian, but they tune it properly too, and they get a point that extrapolates to the same one. That's the good old universality at work, right? What we do is something different. You take a different thing. It's not even an SU3 group, it's something else. And we get something that's wildly different, but seems to be converging to the same answer. Is that the solution to all problems? Not really. Because this last point here is the last point we can use. There is no way to tune this Hamiltonian to get to the true continuum limit, even in principle. So if the lattice space is too fine, the size of my hadrons, my proton, has to be bigger and bigger in lattice units. But it can only be as big as, I don't remember the number, 23. Beyond that, there is nothing you can do about it. So if you're content with this level of precision, that's how you do gauge theories on a quantum computer. But of course, would roughly correspond to this kind of lattice spacing that seems small, but we do better with regular computers. So anyway, it's kind of a mix. I think it sucks. I think it's bad. Nobody's going to invest, years of your research to something is going to eventually fail. Okay, a better truncation. Going back to the sigma model. This is the most popular truncation of every model in every quantum computing paper you're going to see. Okay, it's based on the following idea: a wave function at one point is a function of a direction on a sphere, and you can always expanding the wave function in spherical harmonics. Well, we can truncate this space, put a maximum angular momentum. Then you have a Hilbert space that's finite dimensional. And then you run with it and see what happens. Okay? And that's perfectly fine if you're doing rough calculations. But if you try to go to the, wow, yes, sorry, I hate these buttons. Yeah. There is one thing to worry a little bit about this approach, is that if you take a wave function that's restricted to a certain value of angular momentum, and you multiply by n or take derivatives, apply operators to it, you get a wave function that's not constrained in that subspace. So if L is, for example, L max is equal to 2, when I multiply by n, I get a wave function that includes L equal to 3. But this is not in my Hilbert space. So you throw it away and hope for the best. Okay? Well, you can hope for the best, but it doesn't work. So people have done the following calculation, not in quantum computers, but they put this Hamiltonian. You can do direct diagonalization. Either you have to go to do using tensor networks, et cetera, et cetera. There's some technology here. But you can find what correlation lengths or masses are in this theory as a function of G. You expect that as G becomes smaller and smaller, that corresponds to the lattice spacing becoming smaller and smaller. And what you find is that instead of the mass or the correlation length in lattice units to go to 0, it approaches a certain constant. So that's another way of saying that there is no continuum limit. The duck can never be larger than 13 lattice spacings. So you cannot describe the duck in the continuum limit, because at some point, the duck is going to be 100 lattice spaces. That's what everybody does, by the way. Okay. So there's no continuum limit. There is a way of bypassing this. That's the following. This curve here was done with L equal to 1. The maximum L is 1. If I did L equal to 2, the curve would go a little lower. And if I did L equal to 20, it would go a little lower. Since there is no limit for L, can make it larger and larger, I could approach the continuum limit by doing this. I take an A, do a calculation, then increase L. Then I can go to larger A. And I keep increasing L as I decrease A. The problem with this is that the number of gates is going to grow with the angular momentum, because the Hilbert space at every site is growing, quadratically, in fact. So the number of gates necessary to do a single step in a single site is going to grow too. Now, I used to think by doing just simple calculations that the cost of the number of gates necessary would grow exponentially with L. And if that's the case, that's what I promised to you. If that happens, we lose quantum advantage. I was told that at least in some interesting models, I was wrong. This is not exponential, and it's a mere 14 powers. So if you're content with 14 powers, plus whatever powers you're going to find because of other issues, then that's fine. There is a third way. Yes.
So how does the error, how should you grow L if you want a particular error? Like how does L grow with the error addition? Like
I don't know.
Expectation.
I don't know. This is very dependent on the particular way you discretize, so I don't know the answer. I just know how it scales with the continuum limit when A becomes smaller.
Do you know how small you want A? Like do you want how your error depends on A? Or how
Yeah, so there is a relation between the error you can accept with the value of A. So you have to put all those things together. But all those things are going to be polynomial, so I didn't bother. Yeah, but if there is an exponential cost before. Anyway, that's the way that I thought about figuring this out. So that's the old model, right? At every point, I have a unit vector that lives on a sphere. These three components of this unit vector satisfy a constraint, obviously. And the wave function for a single site can be expanded in those components as a Taylor series. And the Taylor series never ends. That's what makes this space infinite dimensional. Now, someone who was not me invented this weird mathematical construction, not thinking about this at all. It's a string theory thing. Okay? They thought like this. Well, you know, I know three things whose square, they square to 1. They're called Pauli matrices. So I can think of my wave function as a function of Pauli matrices. The difference is that this Taylor series here, when I expanded the wave function in powers of sigma, it ends at this first order. because when I square a Pauli matrix, I get the identity. So if I think of my wave function as being a 2 by 2 matrix, I'm gonna sort of mock up. It's gonna be a truncation of this thing here. Now I took Pauli matrices, but I could have taken the generators of the rotation higher dimensions or higher representations. Everything here would go. This stereo series extend a little further, but it still be finite. My wave function would be larger, but it would still be a finite matrix, yada, yada, yada. So that's a way of discretizing the sphere. The beauty of this is the following. When I discretize the sphere, putting some points here, I get some platonic solid that's not spherical. In this construction here, you'll never break rotational symmetry. You have exact rotational symmetry. So it's a way of substituting a space by a space that's discrete without breaking the symmetries. What's mind-boggling, but it is true. And it's well known. It's called non-commutative geometry, in case you know what it is. I barely do myself, okay? It's easy to see that if I take representations that are bigger and bigger, I can reproduce this exactly. But what I'm interested is in the following fact. So first of all, contrary to the other discretization, if I take a wave function multiplied by a field operator, I just get another 2 by 2 matrix. There's no further truncation. The thing that worried me before is not an issue anymore. But nothing of this matters. What really matters is this. This is going to inspire a certain Hamiltonian. And the question is, does this Hamiltonian have anything to do with the sigma model I wanted to describe to begin with? And my answer is going to be no, it's a different model. It's called the fuzzy O3 sigma model. However, it's going to have, and you can simulate with quantum gates and do the usual stuff that people do. But contrary to the L truncation, my model, if I just stick to Pauli matrices, don't take anything bigger than that, and I take the regular continuum limit of the space-time, they approach the same thing. So first of all, the correlation length in the masses in lattice units do go to 0 very fast. So the model becomes critical. It has a continuum limit. I can describe ducts no matter how fine my lattice is, because I can always make my duct to have a billion lattice spacings by making my G smaller and smaller. It's actually better than this. It's not only that it has a continuum limit, but has the correct continuum limit. I'm not going to try to explain this curve because I think I'm running out of time.
So
Yeah.
Truncations have like something you could dial to make it sort of closer and closer to the original rotor.
Yeah, today
There it was like in the second it was L, but is there something here you can dial or no? It's just one possible.
it's unnecessary. Of course you can. You can take bigger representation,
Okay, it's possible it's unnecessary.
but you can stick to the lowest representation.
It's still
So you never increase your Hilbert space. So you never increase the number of gates, and it works. Okay.
So this describes a different model from the one you sort of said. How
At short distances, but what I'm going to argue here is that at larger distances, it matches exactly the sigma model. So the continuum limit in space carries the continuum limit in the field space automatically with no extra cost. So the exponential or 14 powers of L extra cost that would have other ways is not there anymore. And I think you keep your hope of quantum advantage. I don't know for sure, but you keep your hope, right? So this is called the scaling curve. I can explain if anybody's interested. But the blue thing is what the sigma model does. You can do this. It's a solvable model. You know this curve exactly. And those are results of calculations of the fuzzy model. And the fact that they kind of hug this blue curve is the evidence that I have not only a continuum limit, but I have the correct sigma model. Now, a fantastic thing is that this weird construction using fancy non-commutative geometry, at the same time, another group at Duke and Los Alamos, they had the same idea, except that they had no inspiration on any of that. They just wrote all possible Hamiltonians and start simulating and use some intuition, and God knows they can't explain to me how they did it. And they got the same Hamiltonian, essentially. It's completely no obvious they're the same. It took us months to realize that there was a transformation between our Hamiltonians. But it is the same, so you don't have to fight too much. And that's the same calculation they did now. In their model, they can do Monte Carlo. And the fact that these points are approaching this black curve is evidence that they're the same universality class too. Not the same model, right? except that their evidence is better here. My evidence was better here. So there are like complementary calculations.
Small then?
Sorry?
What's small then? Small.
Yes, that's supposed to be like the mass of the particle, 1 over the size of the duck. You know, it's supposed to be whatever observable you have that has a dimension. So this thing here will describe this model in a tiny little box. So the analog of QCD will be in a box that's smaller than a proton. And this other corner here will describe a bigger box, much larger than the proton. And you want your theory to be describe all of that. You have to agree with the original model that you want at all distances. And that's what this shows, even though I'm being very, anyway, I'm not explaining anything.
So this is though like in L space a little bit, not in like real space.
Now this is, oh, that's a very bad thing I did. This L is the size of the box, is not the truncation. Remember, I don't like truncation. I mentioned the truncation just to poo-poo on it, okay? It's a very bad
I
name.
feel like
I
the
mixed two
L
talks.
is kind of different than the L on the axes. Oh, okay.
I know, sorry, apologize for that. That's amateur hour here. Anyway, all those calculations are done in classical computers, known as my laptop. I think it can be done in an actual quantum computer. So this is the result here, is the result of calculating the mass of my particle, the size of the duck, as a function of g, in a tiny little 6-site model. 6 sites is good because the Hilbert space is 2 bits. I can direct diagonalize this in my laptop. So I know exactly what the gap is going to be, and those are the dotted points. Now, close to very small g, since you have always 6 sites, if g is small, the lattice spacing is small, so the box is small. If the box is small, in asymptotically free theory, you should be able to use perturbation theory. And you use perturbation theory, and you get this blue curve. On the other hand, when g is small, the lattice spacing is larger. So 6 lattice spacing is reasonably large. And then perturbation theory should not work anymore. In fact, I know how it should look like. It should look like this non-perturbative function here.
G is large.
Yeah. Yeah. And so that's the yellow curve here. And what I'm showing is that in a 6-site model, I can show the transition between a perturbative small box to a non-perturbative large box. All you have to do is to be able to measure this quantity to this level of precision in an actual quantum computer. What's a little bit of an heroic effort, but it's not completely insane. I have no idea how I'm doing time.
Few more minutes.
Oh, right. Now, the sigma model is just a little toy. It's a solvable model. Nobody cares. We know everything about it anyway. The question is, are we learning lessons that we can use to interesting problems like gauge theories? It's the only thing that matters. Well, yes and no. So this construction of taking the sphere and substituting by this so-called fuzzy sphere can sort of be generalized. So you take the group, in our case, we took the SU2 group of gauge theory and made it a fuzzy SU2 and created a gauge theory out of that. And we wrote a Hamiltonian, and it's totally speculative. Okay, I have no reason to believe that this non-commutative construction is the actual reason that we got the correct universality class. For all I know, I stumbled on something out of stupidity and I got lucky. Okay, but how can I not try? So we did it. We did it with gauge theories. The problem with gauge theory is that you don't want to study gauge theories in 1 + 1 dimension. It's a stupid theory. You want to use it in 4 dimensions, 3 + 1, because then you have an asymptotically free theory. Also describes the world we live in. Okay? The calculations I did with the fuzzy model were done in 1 dimension. So even if I want a very big lattice, there is technology, numerical technology to solve this model, namely, tensor networks and stuff like this. The analog for 4-dimensional gauge theories does not exist. You say, can't you do Monte Carlo? No, there's a very bad sign problem. Because every interesting problem has a very bad sign problem, right? So I apologize for showing this. This is the result of actually calculating exactly when I have a single plaquette. So gauge theories are not defining points. They're defined on little squares. And you put the squares together and make cubes and hypercubes, and you made space-time out of them. This is the result of a single plaquette. So it means nothing, but I'll show you it anyway. And what I can show you is this. I can do, this is truncation now. This is angular momentum, it's not the size of the box. You can do an L1 truncation, and you'll find is that the correlation lengths or the masses go down as they should, but then they shoot up. And I can do a little better if I do a finer truncation, but it always goes up at the end. On the other hand, if I do this fuzzy gauge theory, it shoots down. This is not zero, this is exponentially small. It's exponentially exactly the way it's supposed to be, but it's one plaquette, so God knows. So anyway, that's the end of my talk. There are some very generic conclusions there that are not worth reading. If you have any questions. Yeah.
So that's all time evolution aesthetics.
So after you have the formulation, and you manage to put this in a quantum computer, sure. That's the goal, right? That's the goal. Yeah. See, we have a Hamiltonian. So, you know, from there on is the usual stuff. Yeah.
Sigma is same as the spin half n Heisenberg chain, right? When n is large. So if you,
Yeah, there's a long story there. That's where the good, interesting theory part is. So when you write our fuzzy model, what you find out is the degrees of freedom are no different from a Heisenberg model. Actually, they are different. Can you see down here? Okay. So in the Heisenberg model, you have a spin, another spin half, another spin half, and say it's a chain like that. Okay. This fuzzy model, if you use in a particular basis, it's equivalent to have another spin here, another spin there, and so on. These spins are connected to these other ones, but they're not connected among themselves. So the Los Alamos people call this the Heisenberg comb, because it looks like a comb, okay? So the coupling between these two things here go like 1 over g squared, and therefore becomes stronger when g becomes small, close to the continuum limit. The coupling in this direction here is proportional to g squared, and therefore becomes weaker in the continuum limit. So what happens is that close to the continuum limit, you essentially have a Heisenberg model. But it's not the Heisenberg model. The Heisenberg model is not critical. There's no continuum limit in the Heisenberg model. What happens is that the ground state is the ground state of the Hilbert of the Heisenberg model times any state for this part here. So there's an exponential degeneracy here. So when you include these couplings here as in perturbation theory, you have degenerate perturbation theory with an exponentially large number of degeneracies. So this perturbation becomes relevant. And then you get this other model. So the Heisenberg model is the same thing as the O3 model in the extreme infrared. This is equal to this sigma model, not only in the extreme infrared, but also in the intermediate region where the masses are. Yeah.
Have you included fermions at all? And are you able to extend this to SU3? Is that picture clear on how to do that?
I mean, the SU3 part? No, there's nothing clear here.
Okay.
So even the proposal for SU2 that does include quarks is a proposal. I don't know how to do a calculation to prove it. I feel in my bones that there should be even a non-numerical, an analytic way of proving this, doing some RG argument. I have not been able to do it. I don't know how to simulate it. So adding quarks is going to be like a frosting on the cake.
So
Everybody knows how to put quarks. Yeah, the quarks are trivial. Yeah. The quarks are, nobody expects any. I mean, except for the usual difficulties of fermions in 3 dimensions and that kind of stuff. Yeah. Yeah.
Suppose I have a model that's built up harmonic oscillators, and then I would imagine kind of if I want to study the higher and higher energies, you know, I need to do truncation of, say, the Fock space at higher and higher end. Like your thing is kind of miraculous. It doesn't need to be like scaled up and up to higher energy questions I'm asking. Is there some place for harmonic oscillators as opposed to like only 3?
This is magic, but not as magic as you think. Okay. So my model is not the same thing as the O3 model at arbitrarily short distances. It is not. There's no magic here. We are truncating the Hilbert space. So the high energy stuff is wrong.
I see.
Okay. I don't know what would be the analog for a harmonic oscillator or simple quantum mechanical system like this, because it very much matters that you have a field theory. that you're going, it's the continuum limiting space that, yeah, I don't have an analog, so.
You don't go to higher and higher representations on this.
No, you can, but why bother? That's the advantage compared to the truncation. So the same code, it doesn't matter what A is, my gates are the same. There's no increase in the number of gates, so there's no 14 powers of L. That's the idea. Also, I don't know how to do gauge theories. Right? Yeah.
So one of the things we're interested in was time evolution.
Yeah.
So offhand, you said if you go for longer times, it is somehow probing like the lower energy.
Yeah, there's a lot of caveats to that.
But like, is this going to kind of like?
It's not going to break down there.
Okay.
If anything, it's going to get better.
Okay.
If anything, it's going to get better. Everybody knows how to get the very low energy stuff right. The quest is to get this intermediate region here, where asymptotically freedom sets in. So in the language of QCD, would be length scale of the size of the proton, or smaller than that. Not the cutoff. Cutoff is non-universal, but the size of the proton, that's a different distance. Fluid dynamics of water that's also made of protons and neutrons, that's easy. Sorry?
Publication of your work?
Yeah, write papers. And sorry?
Have one on this?
We have, there's a few of those papers, yeah, and then there's a few of these other competitors, the Duclos Almus people, that are completely orthogonal way of doing essentially the same thing. And there are papers that followed up that, but not as much as they should. But yeah.
For another question, this is more equivalent to just like ground state. You're like said like higher energy.
Yeah.
No. It starts bailing.
So I get all states whose energy is much smaller than the cutoff scale. In other words, all states that matter.
Right. So like easiest thing, ground state, of course, and then
there's no reason to stop at the ground state.
Well, okay, so like practically speaking, how is there like?
So after you have a Hamiltonian, you're going to put it in a quantum computer. It's a Hamiltonian like any other. It's hard enough to prepare the ground state. It may be hard to prepare other states. This is no different from any other. Although it's a very, very simple Hamiltonian, I claim it's simpler than the original model. For the gauge theory, that's an obvious fact. But all issues are there. Okay, you still have to prepare the ground state. You have to measure stuff. Same thing. Okay, I'm trying to solve one problem, not all of them.
Oh, yeah.